Alright, let's do more on relative motion. So, last time we did this whole thing where we had, say a platform, and we had the ground. I'm drawing these in a little different positions, and it'll become obvious why in a second. So we call this P, we call this G, and there's a guy on the platform who's sort of kicking a ball, and there's the ball B, and that's going up at V naught. V naught is ball's initial velocity, V relative to the platform, and the platform is at some height h, and there's a guy on the ground, and we have different reference frames for these guys. So there's y for the guy on the ground, there's y for the guy on the platform, and it's all, and so we showed how positions can be translated from one to the other. So the platform guy's frame, for example, the initial ball height, well, the position of the ball in the platform frame initially was 0. In position of the ball in the ground frame initially was h, and then the position of the platform with respect to the ground times 0 was h. Whoops, was also h. The platform is h off the ground. There we go. And the ball was starting on the platform, so its position with respect to the platform, y ball platform was 0, y ball ground was h, y platform ground was h. And we also showed that with this notation system you can put together something, an equation, ybp plus yph equals y, oh, I'm sorry, not bh. This thing only undoes like 4 times. It's annoying. So you could show that y of the ball in the platform frame plus y of the platform in the ground frame equals y of the ball in the ground frame, because these two inner subscripts match up. So it's sort of like, you can think of it like they cancel out, and it tells you how to make a valid equation provided you're doing addition. Okay, so this was all good, and this was about as far as we got last time. So now what I want to do is say, what if the platform is moving upward at some constant velocity? So we'll call that VP. VP equals constant velocity of platform with respect to the ground. So the platform is moving up at some constant VP with respect to the ground. How does that change things? Oh boy. Well, so what we can do here, starting from here, we'd have this equation. Okay, can we translate this somehow into an equation that relates to the velocities of these three things? Well, in fact, we can. So the way to look at it is this equation, and I hope this gives you sort of an intuitive feel. This isn't exactly, I'm not sure this is exactly mathematically rigorous, but it's intuitively correct, and it should help you understand what's going on. So we have this equation here. This is not an equation that's true at some instant. It's true for all time. As long as there's a ball and a platform and a ground, their positions, one-dimensional, will be related by this equation. So you can take this, and I'm going to switch to blue here just for fun, and you can say, well, so this equation is true for all time, right? Well, then that means if the left side changes a bit, so delta, and we put the entire left side in there, ybp plus ypg, if that changes, well, the right side has to change by exactly the same amount. That makes sense, right? This is going to be true forever and ever and ever, which means if this side of it changes, this side has to change by the same amount. So if we have a change, over some period of time, then it's easy to just say, well, this changes must be the same. So now that we've gotten that far, what can we say about this stuff on the right? Well, the change in, this is y of the ball with respect to the platform and y of the platform with respect to the ground. So this quantity here, this is the sum of the two. If this changes, then these two have to be changing in ways that add up to the total change. So, an easier way to say it is that you can just distribute the delta over the sum, and like that. Because you're saying if this thing inside changes, then the amount it changes by must be equal to the sum of the changes in this thing. So if this thing increases by 1 or whatever, this must increase by 1, or this must increase by 1, or they must each increase by 0.5, or some other combination that adds up. All right. Now where are we? Well, we're going to say this happens over some period of time. And at this point, actually, all you do is just pull your delta t out, which is the amount of time that passed for this to happen, divide everything by delta t. What's change in velocity divided by change in time? Or sorry, what's change in position divided by change in time? Very simply, it's velocity, right? So what this gives us is velocity of the ball with respect to the platform plus the velocity of the platform with respect to the ground equals the velocity of the ball with respect to the ground. That's almost too easy, right? But it's true. And if you've had calculus, you could just say, well, duh, you take the derivative with respect to time on this equation and you'll get this. And that's true. I just led through the non-calculus way of understanding it, but absolutely it's true you can get here through calculus too. So at this point, the velocity of the ball with respect to the platform plus the velocity of the platform with respect to the ground equals the velocity of the ball with respect to the ground. So initially, the ball has some velocity relative to the platform. So I'm going to drop this down just a wee tad so we get a little space. There we go. Okay. So initially, let's switch to green now. Velocity, so tell you what I'm going to say, at time t equals 0, I'm going to say we knew that the ball initially had a velocity v naught with respect to the platform. So velocity of ball or the platform equals v naught. And the velocity of the platform with respect to the ground equals, well, at all times it equals v sub p, right? So so that's the velocity of the ball with respect to the ground. I'm sorry, I didn't put the g in there. I don't know why. I might have hit, let's see, that was a little better. I might have hit the undo button a little early. So at time t equals 0, what is v velocity of the ball with respect to the ground? We don't know. Well, actually we do. We can take this equation, vbp plus vpg equals vbg. vbg is what we want to find. We know vpg, and we know vbp. So we know the ball's initial velocity with respect to the platform. We know the platform's velocity with respect to the ground. We can find the ball's velocity with respect to the ground. So velocity of ball with respect to the ground equals these two things added up, which is just these two. So vp plus v naught. And that gives us the ball's initial velocity with respect to the ground. So what it means is this guy sitting here is kicking the ball up. While this platform is rising, it appears to him to have an initial velocity of v naught, relative to him. Say if this platform was part of a closed-in elevator, for example, and he couldn't see out, it looks to him like he's kicking it up at a velocity v naught. But if this guy has magic glasses that can see in, so the elevator is rising for him and it's being kicked up by this guy. So the initial velocity of the ball with respect to him appears to be the sum of those two. And that's all this is. So next I'm going to go into acceleration, and then we'll have some examples in 1 and 2 dimensions, I think.